Does the brightening of Betelgeuse herald the imminent occurrence of a new galactic supernova? Betelgeuse is at it again. Back in 2019, the red supergiant star, the bright and iconic right shoulder of Orion, had dimmed dramatically and uncharacteristically, resulting in a flurry of speculation that the star was about to end its life in spectacular fashion as a Type II supernova. That didn't happen. It was later determined that the star had sustained a large mass ejection, partially eclipsing the star and thus reducing its apparent brightness. Fierce stellar winds and large-scale mass ejections are consistent with the behavior of high-mass stars nearing the end of their lives. Welcome, friends. Dr. James Daly, your host here, to discuss the latest uncharacteristic brightening of Betelgeuse and what portends for that star's near-term evolution and possible supernova. Before we do that, though, let's take a look at the evening sky leading up to this year's summer solstice on Wednesday, June 21st. As the sun sets on the summer solstice, we see the moon right to the east with Venus following. Okay, beginning of astronomical twilight, we can see Mars prominently placed to the east of Venus and the moon. And then to further east still, we have Regulus, the heart of Leo the lion, right here. Okay, and we're talking about Betelgeuse in this video, so let's back the sky up a little bit, about 30 minutes at least. Okay, we're going to see where Orion is, and Betelgeuse specifically, the right arm of the Great Hunter. Okay, what we're going to have to turn off the atmosphere. We'll be able to see it much better. We'll be able to see it. Okay, Procyon is a winter star. That's Canis Minor. Here we are backing the sky up without the atmosphere. Okay, clearly this doesn't happen in nature. We're able to do this with this stellarium, digital planetarium. Free download, free software. It's a great tool for those who want to learn the sky, or for professional astronomers and amateur astronomers who need an accurate, concise, an accurate guide to the night sky. So here's Betelgeuse. Okay, it's within less than 10 degrees of the sun. So clearly, if Betelgeuse were to go supernova now, you would not be able to see it at all. Okay, either from the ground or for our orbiting observing platforms like the James Webb Space Telescope or the Hubble Space Telescope, because the pointing rules, the pointing regulations for those telescopes strictly prohibit any targets within 55 degrees of the sun. Okay, clearly this is much closer than 55 degrees. So although there is a special override in place, a rule for overriding this restriction, whether or not a case could be made for observing Betelgeuse as a supernova, that's not clear if we could actually make that case. So that's where Betelgeuse is. Now let's turn the atmosphere back on, and we can see where we were, or where the sky was when we began. Okay, so here's the atmosphere. This is 5:20 in the afternoon, okay, on Wednesday, June 21st, the summer solstice for 2023. Okay, so let's forward the sky, let's advance the sky, and see where it is, and see what it looks like after the sun sets. Okay. The sun is setting. Here we have the moon flanked by Venus, as we mentioned. And there's Mars coming out, will be coming out. There's Venus. There's Mars. Okay, and this is where we were. Okay, so clearly Betelgeuse is not visible. Ground-based observations, no matter where you are on the planet, because it won't matter where you are on the surface of the Earth. Betelgeuse, the Earth is positioned relative to the sun, with the sun relative to Betelgeuse, such that it's out of our sight. It's out of our. It's invisible to see. It's impossible to see because of the position of the Earth in its orbit around the sun relative to the background stars. Okay, so Betelgeuse, even with our orbiting observing platforms, as we said, it would be unavailable to see. All right, so this is the western sky following sunset, astronomical twilight now, which is about an hour after the sun sets. We have the moon, beautifully placed. Here's Venus, Mars, and this is the spring constellation Leo the Lion here. This is the heart of the Lion, Regulus. Okay, here's Virgo up in here with Spica, and further east we have the stars of summer. Here's Antares, Scorpio. This is the heart of the Scorpion, Antares, another red giant star, by the way. And further over here, here's Altair, and which is a member star of the trio known as the Summer Triangle, Altair, Deneb, and Vega. Okay, so this is the sky on June 21st, 2023, the beginning of summer, the first day of summer, the longest day of the year, and the day the sun reaches its highest point in the sky relative to the southern horizon. Okay, so longest day of the year, the shortest night, longest day. Orion is a winter constellation, so those stars are invisible, and if Betelgeuse were to explode now, it would be very difficult, if impossible, to observe for at least the next 2 to 3 months. Since Betelgeuse and the stars of Orion are very close to the sun in the sky, the Hubble Space Telescope and the James Webb Space Telescope could not be used. The Hubble Space Telescope cannot observe any object within 55 degrees of the sun on the sky, for obvious reasons, and there are similar restrictions in place for the James Webb Space Telescope. Although an override exception rule does exist for observations of high scientific value, whether a case could be made to observe Betelgeuse as a supernova is not certain. All stars live and die by nuclear fusion, the only process by which elements heavier than hydrogen are produced. At 15 million degrees Kelvin in its core, the sun is transmuting 600 million metric tons of hydrogen into 596 million metric tons of helium every second. This process, known as the proton-proton chain, has been ongoing for 4.5 billion years and combines 4 hydrogen nuclei, protons, into a helium nucleus. For stars like the Sun, this process continues until there is only 12% of the original hydrogen remaining in its core. At this point, the nuclear fusion reactions begin to abate, resulting in a reduction of the outward gas and radiation pressure, the process by which hydrostatic equilibrium is maintained, the balance between gravitational collapse and unrestrained expansion. The core begins to collapse, but as it does so, it heats up to a point where the helium core that has been built up over the billions of years of hydrogen fusion ignites from the enormous temperature and pressure of the collapsing core, which is 70% of the sun's mass. At this point, hydrogen shell burning commences, surrounding the fusing helium core. There are 2 sources of energy now. The combined energy output from these 2 sources causes the sun to expand to a subgiant star, at which point helium burning stabilizes for about 10% of the sun's original lifespan, between 100 million and 1 billion years. Mercury and Venus are engulfed, and the Earth is sterilized. This triple alpha process continues, producing carbon and oxygen. It continues for another 100 million or 1 billion years, in the process producing carbon and oxygen. Once the helium has been exhausted, the core collapses again, but lacks the mass necessary to ignite the carbon and oxygen and continue any subsequent alpha burning cycles, and a white dwarf star remains with an expanding shell of gas that used to be the sun's outer layers. This planetary nebula is the end state for stars such as our sun. For higher mass stars, stars like Betelgeuse, the alpha building process continues, producing heavier and heavier elements, with the highest mass stars, such as Betelgeuse, continuing all the way up to and including a silicon burning cycle that lasts 24 hours, resulting in the production of metals such as chromium, titanium, iron, and nickel. This is the nuclear end state for all high-mass stars, resulting in a Type II core collapse supernova. The endothermic nature of iron is such that it produces less energy during fusion reactions than it consumes. This property of iron results in an immediate collapse of the high-mass star's inner core. All outward support vanishes, and the imploding outer core rebounds off a degenerate nickel-iron inner core, releasing all the pent-up gravitational potential energy in a maelstrom, obliterating the star and leaving behind a black hole or neutron star in its wake. This is the fate that awaits Betelgeuse and all high-mass stars greater than 8 solar masses. Current estimates put Betelgeuse at about 10 solar masses. And some context is necessary here. There are 2 conflicting studies. The first study, published last month by Hideki Sao and his team, claimed that Betelgeuse is in the latter stages of carbon burning and will reach its nuclear end state and go supernova within years or decades, not centuries or more as was decided following the star's 2019 dimming. Recall we had mentioned hydrostatic equilibrium, the dynamic process where the balance between gravity and outward expansion is maintained. It has long been observed that Betelgeuse, a red supergiant star and well-known supernova candidate, fluctuates in brightness. The observed fluctuations are consistent with and the result of this changing balance between outward pressure and the crush of gravity, a dynamic that is now highly exacerbated by the star's near end-of-life status. With each successive transition to a new fuel source, the byproduct from the previous burning cycle, the cycle time is reduced dramatically. For instance, the silicon burning cycle is only 24 hours and produces, as mentioned, chromium, titanium, iron, and nickel. Stars with an initial mass of about 20 solar masses, such as the case with Betelgeuse, have productive lifespans in the tens of millions of years, not to exceed about 20 million years. Compare that to the Sun's productive lifespan of about 10 billion years. If Betelgeuse is in the latter stages of carbon burning, as is claimed in the first paper by Sao and collaborators, then a supernova is imminent, within decades or within the lifetimes of anyone watching this video. The carbon burning cycle for a star in the current mass range of Betelgeuse is about 100,000 years. The claim in this paper is that Betelgeuse is at the end of its carbon burning cycle and that a transition to a new fuel source such as neon or silicon is underway. If true and the new fuel source is silicon, then a supernova may have already occurred and we're just waiting for the light to travel the 425 light years for us to witness this terrible spectacle, terrible in its sheer power. No matter when it occurs, it will be as bright as the full moon for weeks or months and visible during daylight hours. The second team, headed by Laszlo Molnar, Meredith Joyce, and their team, argue that the fluctuations, which Sao had cited to support his hypothesis that a supernova is imminent, were not primary pulsations but secondary in nature, and thus support the 2019 conclusions that Betelgeuse has many more thousands of years left on its internal clock. The problem is that galactic supernovae are exceedingly rare, and it's almost impossible to model what you can't see. In a given galaxy, 1 or 2 supernovae occur within a century, with the last major core collapse supernova occurring in 1987 in a satellite galaxy, to us, technically not within our galaxy, but in a satellite galaxy, the Small Magellanic Cloud. Being 425 light-years distant, Betelgeuse will provide a spectacular light show when it finally explodes as a supernova, but with no threat to life on Earth, and only time will tell which of these 2 studies is correct. To get a sense of the size and power of Betelgeuse, we'll replace the Sun at the center of the solar system with that star. Let's see what happens when a 10 solar mass red supergiant star is placed in the center of our solar system. at the size of that behemoth. Here's the orbit of Saturn. The orbit of Jupiter is just at the outer boundaries of the star's equator. You see the flares and the prominences leaping off the red supergiant's surface, the photosphere. All the planets, this is, now you have to remember, the Sun is a 1 solar mass star by definition. This is a 10 solar mass star. So you're replacing a 1 solar mass star with a 10 solar mass star that's many hundreds of times bigger. It's going to completely disrupt the entire solar system. This would never happen actually in nature, and the Sun would in fact never get this big. The only reason the Sun's not going to get this big is it only has 1 solar mass. When it exhausts its hydrogen and starts to burn helium, at that point it'll swell to a red giant star. This is a red supergiant star. It's huge. Okay? Look what happens to the planets. Look at the prevailing temperature on Saturn. Click Saturn here. It's going to list the temperatures for Saturn. Here, what's the temperature for Saturn? Average temperature at Saturn is almost 800 degrees Celsius. Okay. The rest of the solar system is destroyed. This is just a hypothetical to show you what would happen, and the comparative sizes of a red supergiant star and a regular main sequence star like our Sun. Look at Pluto. Here's Pluto. Click Pluto and see what the prevailing temperature on Pluto will be. 343 degrees Celsius. It's 250 degrees above the boiling point of water on the surface of Pluto. Let's see. It'll tell us also how far our observational standpoint, our observational viewpoint, are looking at the star, how far we are from the star's photosphere, its surface. It's 4.25 astronomical units in radius. Okay, that's 4 times the distance from the Earth to the Sun. Our vantage point is 37 astronomical units. Which is 10 times the star's radius. So we're at this viewpoint right here, we're 10 times the distance from that star that the star's radius is. 37 astronomical units is 10 times the distance to Jupiter. The distance to Neptune is 30 AU. So right now we're 7 astronomical units further than the distance to Neptune. Right now, as we see this star at the center of our solar system. This is Dr. Jim Daly of Astronomy for Change. May you come to love the stars too fondly to be fearful of the night. And remember, the Earth is a mote of dust floating in a sunbeam. That's reality. Everything else is just marketing. The great philosopher Plato famously said, "Astronomy compels the soul to look upward and leads us from this world to another." Astronomy for Change is a non-profit organization whose mission is to effect a positive change through astronomy and science education. It is our belief that by inspiring and empowering current and future generations to become interested and engaged in astronomy and science, this positive change will be realized. If you found this video helpful and educational, please like, subscribe, and share. Also, why not consider supporting us on Patreon? Head over to our homepage, astronomyforchange.org, click Support Us via PayPal or Patreon, and choose a membership level suitable for you.
Every little bit helps us produce the great content and further our mission. Also, why not consider becoming a member? Choose the membership link here, click it, put your name in, your first name and your email, and you'll be added to our list. You'll receive a comprehensive digest of all our videos and articles and all our great content. Joining and becoming a patron helps us grow and improve and more fully realize our mission. Thank you.